3 deals with reactivity, which is kind of what we've done basically all year so far. We've talked about periodic trends and why things are bonding. In this unit, we've been talking specifically about redox reactions, and we can do what we learn in redox reactions to make some predictions on how reactive things would be based off of experimental data. So first of all, we need to know what a redox couple is. A redox couple is whenever we have a species that has a standard form that it becomes when it's oxidized or reduced. So some common examples, zinc, even though it's a transition metal, will form an oxidation number of 2+. So we have zinc as a solid, and then zinc with some compound that we don't know what the spectator ion here, but it doesn't matter for us. It could just be chlorine, so it'd be ZnCl2. The oxidation number of the zinc in this ion is a 2+. Zinc here is a 0. So if we're going from, let's say this is on the reactant side and this is on the product side, we're going from Zn0 to Zn2+. We've lost electrons, so it's being oxidized. We could also have this redox couple flipped. So we could have the Zn2+ on the reactant side and Zn0 on the product side. In that case, we would be having reduction. Same sort of thing, sodium is always going to be a 1+ for its oxidation number. So we can deal with the redox couple there same way that we did before. There's certain elements that don't have redox couples because they can form so many different oxidation numbers. For instance, vanadium, which we're going to be doing a demonstration on, comes from the Norse word for goddess of beauty, and they called vanadium after Venus because there's so many beautiful colors that the different ions or the different oxidation states will form for vanadium. So we're going to be dealing with that later, and it would not form a redox couple because of all of those different oxidation states. We can form reactivity series based off of redox couples, so the ones that we know have one standard oxidation number. And if a species in a redox couple is a strong oxidizing agent, then the other in the couple would be a weak reducing agent. And that again goes back to what we were talking about on the other side of we have to be specific about what's on the reactant side and what is on the product side. So much like the reactivity trends that we saw earlier in the year, for instance, the alkali metals are more reactive with water as you go from lithium all the way down to francium, because francium can so easily lose that valence electron. And we know that fluorine is so electronegative, it's going to pull electrons towards it. So the periodic trend on the halogens is that as we go up the periodic table from iodine all the way up to fluorine, it's going to become more reactive. So we know some of those trends already, and we can now link them to this redox rule. And the most common way that we're going to see these redox reactions is when we have a single displacement reaction. So for instance, when we talked about single displacement reactions at the beginning of the year, we said we have some element on its own plus some compound. If there is no reaction, then the element A is not strong enough to come in and kick out element B. It doesn't work for us, so that would be no reaction. What we may see, though, is that, let's say B is on its own, and it reacts with a compound of AC. B, let's say, is strong enough to come in and kick out the A. So now A is all on its own, plus we have a compound BC. So we know that A is less reactive than B. So if I was to draw a reactivity series, and let's say I want the most reactive on top and the least reactive on the bottom, which it's not always this way, but this time we're going to have the most reactive on the top. B is more reactive than A. Now I could have just as easily written out this equation without my spectator ion. My spectator ion here is whatever my C is. So I could have written it that B comes in and reacts with A, let's say the oxidation number is a +1. And that forms solid A plus B, with a +1 oxidation number. So this is probably how you're most often going to see it, where we don't actually see the spectator ion because it's not important for us. But we know if we have an ion that it's bonded to something else, and if it does react, whatever this solid is to start with is stronger than whatever the ion is because it can kick it out. Here's a common metal reactivity series. You have this listed in your notes. Notice that we're dealing with the most reactive on top in this one and the least reactive on the bottom of this one. That's one way to see them. However, not the only way. This reactivity series, we have the most reactive fluorine at the bottom, the least iodine on the top. So it just depends. And this video is linked into the RedOx play group that I have on YouTube, so you can see this one as well. It goes through some interesting reactions, many of which we have seen throughout the year, and talks about them in terms of redox chemistry as opposed to just in terms of